In the previous video, we saw that the definition of the derivative of a function at a certain point is actually a limit. So when you're given a problem which asks you to compute a derivative, the first step is to set up that limit. Later in Chapter 3, we're going to learn other methods for computing derivatives, but in Section 3.1 and on the midterm, we're always going to use this limit definition. And the questions will often say that you should use the definition of the derivative to compute it. So we need to set up a limit, and there are two different styles of limits you can use. You can either take the limit as x goes to a of fx minus fa over x minus a, or you can take the limit as h goes to 0 for f of a plus h minus fa and divide by h. As we go through examples, you'll see pluses and minuses to each one of these styles. Once you've set up the limit, then you need to compute it. Notice that in either case, when x is approaching a or when h is approaching 0, substitution will give this limit the form 0 over 0, which is an indeterminate form. So we're always going to have to start with using some of those strategies for indeterminate forms that we developed in Section 2.5. Then, after simplification, you might be able to use substitution, which we developed earlier in Chapter 2. Pause the video and try to calculate the derivative of f at a for each one of these three scenarios. We start with the example where f is x squared and a is 3. Using the first style of limit then, we want to take the limit as x goes to 3 of x squared minus 3 squared, which is 9, divided by x minus 3. As we observed before, we're always going to get 0 divided by 0 with substitution, so we have to use some of those strategies for dealing with indeterminate forms. And here, since we have a polynomial over a polynomial, and the form is 0 over 0, we want to use factoring. The numerator here is a difference of squares, so factoring pulls out an x minus 3 on top and bottom, leaving just x plus 3, for which substitution gives 6. Now, if you do this the other way, we have to take the limit as h goes to 0, and we're still going to have something minus 9 on top, but that something is now 3 plus h squared. Everywhere we had seen an x before, we're going to put a plus h, which in this case is 3 plus h. Now, if we just expand on top, that constant 9 is going to cancel out, and we have something divisible by h. So factoring will give us a limit that we can evaluate with substitution, and we again get 6. Our second example was the absolute value of x minus 2, where a is 2. When we set up the first type of limit, we're going to get the absolute value of x minus 2 minus the absolute value of 0. Now this limit is secretly about a piecewise function, right? The absolute value of something is really a piecewise function. So we want to use left and right hand limits. When we look at the limit as x goes to 2 from the right, the quantity x minus 2 is always going to be positive. It's going to be a smaller and smaller positive number as x approaches 2 from the right. Since it's positive then, the absolute value of x minus 2 is just x minus 2, and we can see that the limit will just be 1. On the other hand, when we take the limit as x goes to 2 from the left, x minus 2 is always going to be negative. It's going to be a smaller and smaller negative number as x approaches 2 from the left. So what's the absolute value of a negative number? Well, it's that number's negative. The absolute value of negative 7 is negative negative 7. So that minus sign comes out, and in the limit we just get minus 1. Since the left and right hand limits don't match, the two-sided limit does not exist. If you were to use the other style of limit here, you should get the absolute value of h divided by h as h goes to 0, and looking at the left and right hand limits will give you the same thing. The right hand limit should be 1, the left hand limit should be minus 1, and the two-sided limit does not exist. Finally, we had fx is 1 over 2x plus 1, and a is 1. When we calculate the derivative in the first way, we get that function, 1 over 2x plus 1, minus f of 1, so minus 1/3, all in the numerator, and then we still have a denominator of x minus 1. When we try to evaluate this, our first step is going to be to combine those fractions in the numerator and use algebra to make this one big fraction. When you do that, the numerator should become 3 minus quantity 2x plus 1 on top, and on the bottom you get 3 factors, the x minus 1 which was in the original denominator, and the 3 and the 2x plus 1 which are coming from combining the numerator into a big fraction. Now when we factor this numerator on top, we're going to get a multiple of x minus 1, which then is going to cancel out with the x minus 1 in the bottom. Which multiple of x minus 1 do we get on top? We get 2 minus 2x, which is negative 2 times x minus 1. For this last limit, we can use substitution, and so we get negative 2/9. If you did this the other way, the limit you'd be calculating would have still that minus 1/3 on top and an h on bottom. But what about that f of a plus h? What would that equal here? When you carefully substitute 1 plus h for x, you should get 1 over 3 plus 2h. And now if we combine fractions as we did before, in the denominator you're going to wind up with h, 3, and 3 plus 2h. And in the numerator, you should be left with minus 2h. So if you cancel those h's out, and then use substitution, we get negative 2/9 again. Notice that in all of these examples, setting up the limit in the first style was more straightforward because we know what f of x is. It's given to us. Whereas in the second style, you have to figure out what is f of a plus h. You have to make a careful substitution to figure out what that term should be. Since the first style is easier to set up correctly, we're going to stick with it for the remaining examples, which are all a bit more challenging than the ones we've seen so far. Consider this example where fx is the square root of 3x minus 1 and a is 2. To calculate the derivative of f at 2, we start with setting up this limit. As always with derivatives, substitution is going to give us the form 0 divided by 0, but now we don't have a polynomial, we have something with square roots on top, and that reminds us of a strategy we've seen before. That is to multiply on top and bottom by the conjugate of that square root thing, because then in the numerator we're going to produce a difference of squares. The difference of squares here gives 3x minus 1 minus 5, which is the same as 3 times x minus 2. Then the x minus 2 on top and bottom cancel out, and we're able to use substitution to get 3 divided by 2 times the square root of 5. What about if f is x minus 2 cubed and a is 1? Try to set up the limit. You should get this limit, which you may recognize. If you rewrite that minus negative 1 cubed as plus 1, then this is a challenge problem that we had in one of the videos from section 2.5. If we use the difference of cubes here, we end up with this expression, and now substitution just gives 3. When we're using the difference of cubes here, we're saying x minus 2 is a, and negative 1 is b. After we cancel out that shared factor of x minus 1, we get a squared, a times b, and b squared. We can even have examples where we don't know what a is. It's just some unknown constant. If we have an example like that where f is some arbitrary line, arbitrary slope m, arbitrary y-intercept b, when we set up the limit for the derivative, in the numerator those plus b's are going to cancel out, and factoring will pull an x minus a out on top, and we just wind up with m. So in other words, any line with slope m has a derivative equal to m everywhere. This f prime of a does not depend on a. The derivative is constant. This result is called Theorem 1 in the textbook. Notice that when m is 0, f of x is a constant, and so we're saying the derivative of a constant is 0 everywhere. Please go on to the next video where we'll talk more about derivatives in the context of tangent lines.